Hello everyone, July the 6th. Alright, so yesterday was pretty bad. This problem, even after I saw the solution, I still don't understand. I don't understand at all. And I have to really, I think I spent 1 hour at least afterwards just trying to play in my head. What does this mean? What does this mean? I think I got it. I think I got it. But it's a tricky one. It's a tricky one. I'm gonna read more of this, right? Try to fully understand, see if my understanding from yesterday was correct. But the most important, I think, is to do BIT. I want to see how BIT does, because in reality, I think it should be BIT. So we're going to take a look at the BIT. So we probably will spend a long time on this just to figure out. All right, so let's finish today's chat first. Maximize the confusion of an exam. A teacher is writing an exam with n true or false questions, with t denoting true and f denoting false. He wants to confuse the students by maximizing the number of consecutive questions with the same answer. Multiple truths. Oh yeah, that does maximize confusion. That's okay. He wants to confuse with the same answer. You're given a string, answer key, where answer key I is the original answer to the ith question. In addition, you're given an integer k, the maximum number of times you may perform the following operation. Change the answer key for any question to t or f to the maximum number of consecutive t or f in the answer key. So basically we have k number of operations. So we want to make k changes such that we can maximize the consecutive t or f's in the answer. All right, easy enough. If we do this, will be all t's. Change one. Change one. We can do this, but t doesn't. Okay. So basically, let's say we grab the number of consecutives currently, and then we want to change one in this case, and want to maximize it, right? We want to maximize it. So what do you think? Well, we can always do it 2 times because it's t and f, right? We can do it 2 times. One run, we can say I want to maximize t, and the other run, I say I want to maximize f, because it's not going to be true if you're doing some t and some f. That is just not going to work, because if you say I do some change to t, some change to f, and you say that gives me the best, and I can always change both to t or both to f to give you a better one. So so it has to be all t or all f. So we just do it 2 rounds, and the solution is actually the same, right? Okay, so now the question is, how many, let's just think about changing f into t, okay? So if we change f into t, how do we change the k of them so we can make the t, we can maximize the t, all right? So how do we do this? Well, I think we are in the week of sliding window, and we did something similar before. So let's see if sliding window can work. And to work with sliding window, let's just say we'll start with counting the number of F's in the sliding window, okay? So if the number of F's is, so what we want is to have KF's, right, in between some T's. That's what we want. Well, if we have KF's between some T's, now we can change those F's into T, and we can merge the T's on both sides. And when we do so, it will make it longer, right? Make the consecutive T longer, okay? So what we can do is, using the sliding window, we will expand the sliding window. We'll count the number of F's in it. And we only allow K. If it's larger than K, number of F's, we just shrink, right? We shrink until we get, I kind of don't want to do sliding window. I kind of just want to do consecutive. Like we do the group by, we do the Python group by, right? And we just find if there are K number of F's, right? If there are, then we can link the T's on both sides, and then boom, we have it. And if there's no such a thing, then it's gonna be the max count of T originally, then plus. Oh, you could, we can have like smaller than that. Yeah, we can have, hold a second, we can have that. So there are situations, right? We'll come up, what if we have like say T, 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 and F, a T, 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 and F, and T, 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 like that, right? Then you need to change this one, change this one. So it does look like we have to go sliding window, right? Because it doesn't matter where the F's are. What matters is in a window we have two F's, right? So we sliding window, we just have a start, we have I, and we have a J, just keep going. And if we have more than two F's, more than KF's, so we just, keep going. If it's more than KF, we just, this one goes forward, and we keep going, right? Whenever it is KF's, we find the current length, right? And then we always move on, right? And then we will add, more F's. And if it's more, then we will reduce until it's K. And when it's K, we find out. And we go this one round, which checks for F. And we do another round, exactly the same thing. Then we checks for T. Okay, so we can write a function for this and just repeat the function. I think that shall do. Okay, so what do? We will have a def slide. What we want to find is the target. It's gonna be str when we return int, okay? And then we say I equals res equals 0 for j, and also count for j in range. Len answer keys. Ooh, yes. We say count plus equal to, answer key j is equal to target. Okay. And then we say while count is larger than k, I plus equal 1, and count minus equal 2, answer key I equal to target. Right? And then we say if count is equal to k, res equal to maximum res j minus I plus 1. And then when we're done, we return res. Then we'll return the maximum of slide f and slide t. What do you think? Pretty fast in this, the logic is pretty fast, so I'm not exactly sure, but we can take a look. Oh, I should get more. Oh, I have issue. The last one. That's fine. Should be 5. My output is 6. Dude, that is not right. Okay, let's take a look. What did we go wrong? It's okay. It's okay. We'll check. Actually, I'm interested. I'm interested in what did we get wrong. 5. Okie dokie. Answer key. Okay. Max consecutive answer key and k. Okay, so the last one, right? Okay, the last one. So we start from here, right? And we are looking for f, right? We're changing f. So we go ba, 0, ba is 1, okay? And we get 1, and ba, still 1, ba, that's 5. And then, boom, we had another one. Then we need to pop. Right? Well, pop. Maybe what we did is, well, this is larger than k. If this is larger than k, count is larger than k. So we shall pop this, and that's it. You know what? Let's just print. Let's print I, j, and k. No, I, j, and count. Here, we have a 2, 7, 0, 1, 2, 3, 4, 5, 6, 7. How is this counted to 1? Trouble. I think we got this one wrong. It's not the first time that I did it wrong, right? You should remove it first. There you go. Okay, let's try this. Ugh. Edge case. Not edge case. This is... Oh my god. Expected 2. Dude. It is edge case. Holy crap. How did you get it wrong? Well, I never... Okay. Because this shall be if count is smaller, you go to 2. Ah. Dang it. Dang it. Try it again. There we go. It should be smaller or equal to. It's smaller or equal to. That's an oversight. Okay. Let's write some stuff. 2 rounds of sliding window. Yeah. We can swap as long as the count is not bigger than k. Yeah, that's very important. Okay. Take a look at the solution. Binary search, fixed size sliding window. Yes, I can see. So you get, we just need to know the sliding window, and within this window, what is the number of t or k? We just need to find one of them, all right? And if, yeah, we sliding window going through to count how many among all the sliding windows, how many t's or f's is inside each one of them, and to see if it's possible. If it's possible, we can, make it a little bit bigger or make it a bit smaller. Yeah, binary search can do. O1 login. That one can do. No issue. Sliding window. Wow, they slided once. Maybe I can try sliding once. Yeah, we can slide it once. Okay, let's slide it once. One round of sliding window. Oh, you cannot do one round because the window size changes. Then how did they do one round of sliding window? The minimum, look at that. The minimum. Oh, yeah, and I don't have to do this. Dear God. Yeah, I don't have to do this. The count must be smaller or equal to k. So, now the only thing we need to do is... We have a counter. Okay, so we have 2 counts. We want a count t and the other count f, right? And then as we go, we'll increment the count. And as long as the smallest is larger, then we need to reduce. But if the smallest is larger, well, minus equal 1, left plus equal 1. Wait, why? The smallest is larger. So, oh yeah, the smallest, if the smallest is smaller. Yeah, I see. We only need the smallest to be. Okay. That's fine. So, I can do one round. Okay. So, we do this. I res count t count f. So this we say count t plus equal to t count f plus equal to f, while the minimum of count t and count f. Then we'll minus equal to what? Oh, dude, that is not an easy way to go. Okay, so we don't do it this way. Nope. Count T F. Yep, that'll be easier. So this will just plus. So we say count. Yeah, count answer key J plus equal 1. All right. Perfect. And then the minimum of count our values. Then we say count minus count this minus equal 1. And now we don't have to do this. And then rest will equal to maximum rest and this, and then return this. I think that shall be it. Yeah, one round of sliding window. All we need to do is to shrink the window when the smaller of the T or F count is larger than K. Yeah, as guaranteed, as you do this, you're always picking the right target to switch. Oh, I think this one will be faster. I think this one will definitely be faster. Yep. Okay, that's that. All right, let's go back to this. Let's just read other people's, just kind of see. We just find the smallest, second smallest until the nth smallest numbers, and they're just from left to right. Then after n operations, all the other n minus m numbers go back to the correct original position, which is have a shorter array to restart. We find the smallest, second smallest until the mth smallest, and they're just from left to right, okay? The first, the second, just, and then after n operations, n minus m movings. Yeah, because you need to swap this to the end, you remove, swap this to the end, you remove, so that's n minus m movings and m deletions. That's correct. All the other n minus m numbers go back to the correct original positions, which is have a shorter array to start. That's probably the best explanation that I've read. Yep. Yep, this is better than my 1 hour thinking yesterday. Yes, exactly. You just look for the stretch. That's what I was saying. I was talking about stretch. This is a stretch. You find the smallest, the second smallest, blah, 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 until the stretch breaks. And then to remove those, you move things around. And what you find out is after you move things around, the remaining is exactly the same as before. Right? So now you know. And you also know the number of moves it takes to remove the first stretch, right? So first stretch. So what you do is you sort the numbers, right? And if you sort the numbers, you have the smallest, and you just find the first stretch. Where is the first stretch? Well, the first stretch is found. You have the smallest, have the second smallest, right? So if the first smallest, second smallest, they are in the stretch, doesn't matter, and you find something that is bigger, right? But its position is in the previous, so we don't follow the stretch. So when we find something that don't follow the stretch, right? When you find that, then you say we need to remove all the others, right? We need to remove all the others. So what you do is you put these to the end. Okay, then no. Here, no. The idea, no. Hold a second. Let's do this one more time. So we have something. Let's say blah blah blah. We have the 0, blah blah blah, 1, blah blah blah, 2. Right? We have an array like this. So as you go, you will find this position is whatever position, right? And then the next one is this is good. The next one is this. They're all following the stretch. But then you say, let's say maybe 3 is here. Doesn't matter. 3 is here. Doesn't matter where 3 is. And this is breaking. It's breaking the stretch because this is earlier than this. So now we know we want to remove the previous stretch. Okay? And how do you remove the previous stretch? We say we'll move this to the end. Okay, so we have this, right? And remove this. We move this to the end. We remove this, we move this to the end. So this is exactly the same as the original one, except 0, 1, 2 have been removed. Okay? And pay attention, the total number of movement is the number of values that are larger than this 2. So the total moves is this plus the 3 things that we moved, right? And then we just do the same, and then we check 3, doesn't matter if we have some value. Now we have 4 here, okay, it's okay. And then I said we have 5 here. Okay, so this 5 breaks the stretch. So whenever we break the stretch, we have to move the previous one inside the stretch. And how do we do that? We move the things to the right? So we'll move this to here, and I will remove this, remove this. Okay, here is the catch, right? So you remove these 2, and you have to also move all of this to the right. Now, why is that? Why does that? Like, understand this. This makes perfect sense, right? But now you're saying I have a stretch. Okay? I have a stretch. And after the stretch, I have some values as well. And before the stretch, I have some value. Now we have 3 at here. It doesn't really matter where the 3 is. And then I say I want to remove these. I need to put everything here to the end. That I agree. But then all of these has to be removed as well, moved to the end. Now, what I can explain is these things. I mean, you don't need to move these to remove, let's say 0, 1, 2. Yeah, let me do it one more time, right? We have 3 something something 0, 1, 2 something something something. And to delete, so we go 0, 1, 2, they're in the stretch. 3, that's out of the stretch. So we say to remove 0, 1, 2, we need to move this to the end. And in fact, that's it. That's all we need to do to remove 0, 1, 2. So the number of moves is actually not the number of values that's larger than 2. That's not, right? In reality. However, once we turn this into this, 3 something something, right? Once we turn into this, we will have to remove these regardless, right? That's kind of the idea. So you either remove these in the next round, when we handle this, you have to remove, or you remove these in the previous round. Then in the next round, you don't remove. See? That's the thing. That's the thing. You either remove it in the previous round, or you remove it in the next round. You have to remove them, not remove, you have to relocate them at least once. Right? So yeah, if you are heading in this case, now I say I want to remove 3. right? Doesn't matter, 4 can be here, 4 can be here. Now say I want to remove 3. Then you have to move all of these to the end, right? So this gets moved once. If I move it earlier, which means after this, I turn this thing into 3 something something. I would say 4 is here, right? And then something for something. Now, when we go 3 and then we go 4, there's no removal, right? There's no movement. There's no relocation anymore. So that is the reason why. That is the reason why. Every time you need to remove a stretch, you just relocate everybody that's larger than it. And it makes sense. But still, not the easiest one to figure out, but it does make sense now. And like I said, right, all the numbers go back to the original position. N minus M movings. I mean, not exactly N minus M movings, but it makes sense. It makes sense. Because the remaining thing you can choose to move in the current round, or you have to move it in the next round. So it's one way or another you have to remove them. There's no going around, right? Because when you do the move, this is the next smallest thing, right? So you want to move, and if you want to remove this, you have to move these chunks as well. So there's no going back. I would like this solution. Do you want to be a BIT? Go to the first smallest number. The position is 3. And it takes 4 operations. Yes. Going from index current to index ID takes operations. Reduce the number of operations for elements who are already removed. Answer is equal to n, yes, plus number of values greater than the bigger value between any pair of adjacent values in sorted array. Basically, if this is sorted, now initially answer is 4. First pair of adjacent values is 1, 2. So answer is 4 plus 2. 2 values greater than 2. Next pair is 2, 5. No value greater than 5. Between 2 and 5. the last pair is 5, 6. Wait, hold a second. First pair, 1, 2. We need to number greater than the bigger value, because those need to be removed. Let me think. Number of values greater than the bigger value between any pair of adjacent. So we have a pair, the number of values bigger than one of them. Answer equal to 4. Yes, first pair of adjacent values. Is that the number to remove? Remove 2, 1 and 2. The next pair is 5. No value greater than 5 between 2 and 5. That's not true. 6 is in between. Screw this. I am not going to go through the Fenwick tree on this one. Let me just do this one more time. Okay, one more time based on our own understanding. Okay, oh, this one is a hard one. Okay. All right, here it is. Oh, we fail on this one. Good explanation is, I got it from, which one? This one, right? Yes. A good explanation is here. Okay, let's explain. So the idea is that when we want to remove, right, when we have a consecutive stretch, right, when we want to remove a consecutive, how do we say that? When we want to remove a consecutive stretch, okay, when we want to remove a consecutive smallest stretch of values. Well, first of all, the total number of removals will cost ln nums of steps. This is a hard minimum. We cannot get below that. Any additional cost is due to relocation. I don't think they call it relocation. I just call it as a relocation of the values. Thus, we need to find out the number of relocations necessary for each to remove, right, each number, each value. Notice that to remove a consecutive smallest stretch of values, we can relocate all the values larger than the largest of the stretch to maintain, to return the array into its original position. For instance, right? For instance, I will use this and I say A 3 B 0 C D 1 E 2, right? Okay. Where the letters represent some values larger than 3. Okay. To remove 0, 1, 2, which is a smallest consecutive stretch, we need to move A3B. Let's mark them up. All right, A3B, CD, and E to the right. And after the removal of 0, 1, 2, we have A3B, C, D, E, right? Which follows the exact same positions as the original array, except for the removal of 0, 1, 2. Now, interestingly, if we have this case, yeah, that's the one that troubles me the most yesterday. So let's put this one here. Interesting, if we have this FGH, right? We only need to we can remove 0, 1, 2 by turning the array into this, right? We can turn the array into FGH A3B CD EF, right? I think you have more F. No, this is just CDE, right? Now we are not removing all the values larger than 2, right? Larger than 2, because it is not necessary. Not relocating. It's not removing. Relocating, because it's not necessary to relocate FGH to remove 0, 1, 2. However, to remove 3, right? To remove 3, FGH have to be relocated no matter what, because they are larger than 3. So we either relocate them in the next round of removing 3, or we relocate them in the previous round of removing 0, 1, 2, right? Either it's a late round or in the previous round. The effect is the same, but the implication is quite different, because if we relocate them in the previous round, right, we significantly simplify the logic of each round of relocation, right? Each round of relocation, we only need to relocate. We relocate all the numbers with value larger than the largest of the stretch, right? The smallest, oh my god. Largest of the smallest consecutive stretch. Yes, now we just follow this and we'll be done. So that's the case that's, troubling me the most. But now you know, right? We don't have to move FGH. It's okay, it can stay on the front. But if we want to remove the next thing, we want to move 3, then these has to be moved to the back no matter what, right? So I either do it in this round, we do a move, so this will be exactly the same as the previous, except the removal of 0, 1, 2. I can do it that way, or I can do it later. They only gets relocated, like either you can attach the relocation in the previous round or attach it to the later round. Now you attach to the later round and the whole relocation steps gets very complicated. They cannot keep track. But if you do in the previous round, then all the relocation happens on a very distinct number of steps, which is just the number of values larger than the largest of the stretch. So with this in mind, then we can do, right? So with this method, we can solve the problem by sorting the original array with their indices attached. If we see a stretch, right? Actually, it's not even consecutive. Hold on, let me remove consecutive. This is not necessarily consecutive. Wait, what do you mean by consecutive? Yeah, it is. It's consecutive in terms of the values, not consecutive in terms of the positions. So if we see a stretch of smallest values, which means this means their indices increases, we do nothing, right? Once a value has smaller index, right, than its predecessor, that is the signal that the previous stretch can be removed, and the number of relocations is the number of values larger or equal to the current value. Yep. All right, let's do this. So we have nums, so we can say sorted nums equal to sorted for in enumerate nums, and we're gonna do ni because we're gonna sort based on n. Once we're done, we say res equals to len nums. So this is the cost of removal. And now we're going to calculate the cost. So we're going to compute the cost of relocation. So we're going to say for I in range 1 to len nums. Okay. And each time we're going to check if sorted nums I 1, it's its index. If its index is smaller than sorted nums I minus 1, 1, right? So we have a wrong position, right? Not consecutive, not a stretch. When it's not a stretch, we need to compute the number of relocation. So res in the plus equal to the number of relocation is the total number of values larger or equal to sorted nums I, so which is len nums, right? The total minus the index. Yes. So we do that, and we'll return res at the end. Yep, we can check. Oh, this is, I don't know. I mean, technique-wise, I don't know what type of technique you need. It's just observation, right? It's just observation. Man. So you can have as good techniques as you want, but sometimes if you don't have a good observation skill, yeah, this is just not gonna work. It looks nice, right? It looks like, oh, you solve in the first try. No, I did not solve in the first try. This one's tough. Very, very tough. All right, I'm gonna put that one in the nightmare. Nightmare. Ooh. All right. What now? Well, no, we have to start a new thing. Do you want to do it tomorrow? Let's get the questions out, and then we're gonna do tomorrow. Yeah, 22.9%. Yeah. I'll do these tomorrow. I'm hungry. I need to eat, and I need to train. So that'll be it. See you guys tomorrow. Adios.